So, time again for a little quiz. This is the quiz question. If you have two capillaries with a different channel diameter, a large diameter and a small diameter, which one of the two will fill the fastest? The one with a larger diameter or the one with the smaller diameter? Right. Let's have a look at that. If I have a capillary with a radius r, a filling front, I have just calculated that I have a capillary pressure drop here, or a capillary pressure equals 2 gamma cosinus theta over r. And I also know that, if I consider this part of the cylindrical channel here with length L, I also know from the Navier-Stokes equation we derived the Hagen-Poiseuille, and we could derive there also that the velocity U, the average filling velocity in a cylindrical channel with a certain pressure drop, equals delta P times r squared over 8 mu L. And delta P is of course the pressure drop from this point to this point, but I'm going to consider that the pressure at the entrance here is the same as the pressure in the atmosphere here. Again, there's going to be a droplet here, so there's going to be a slight pressure drop here, but because the curvature radius here is so low that this pressure drop, I'm going to neglect that one. So the pressure drop here is actually the same as the pressure drop here, I'm going to assume. And now I know this is my average velocity, and I have my formula delta P here, so I can write this out. This equals gamma cosinus theta over 16 mu L times R. So my average velocity, filling velocity here, will scale with R. That means the larger the diameter of my channel, the faster it will fill. The smaller, the slower it will fill. Now this is a little bit counterintuitive because we see that actually the capillary pressure actually increases here with the smaller r. So the smaller the r, the larger the pressure that drives. However, we see that the fluidic resistance here scales with the power r squared. Yeah? You can even see that more clearly if you take the other formula in the Hagen-Poiseuille where we wrote that there's a relation between delta Q, or we also wrote that delta P equals Q times a certain term, and this term here, we can call that the hydrodynamic resistance, and that one scales with the power 4 of the diameter. So we see that smaller systems get a much higher resistance, and the increase of resistance is larger than the increase of pressure drop. So overall, we see that still larger diameters will fill faster.